In lesson 11.3, we're going to be talking about if you were to plot data, say from a statistical survey you sent out. Oftentimes the data can be approximately normal. That means most of your data will lie in the center. We'll be using your understanding of mean and standard deviation from your previous courses and put them on these normal distribution scales. Now, for it to be normal, we're talking about a nice little bell curve here, and this one doesn't have any skew. If your data is pushed a little bit over here to the right side, we call that skewed left, so it feels a little backwards. If your data is looking like it's pushed a little bit left, we call that skewed right. So kind of think of it too, like your mean is pushed over to the right, your average would be pushed over to the right from where most of your data is. Whereas this one, your mean is pushed over to the left compared to where most of your data is. For mean, remember that's the word average. So mean is an average. If we were going to do this by hand, of all these numbers and take the average, we'd add them all up and divide by how many there are. Now, a standard deviation is talking about how far the data is spread out. So, for example, if you had a normal curve, your standard deviation, say, this is where your mean is always going to lie, right in the middle there of a normal curve. Most of your data is within that first standard deviation. So we'd say this is one standard deviation. It's not very spread out. Whereas if I had a curve like this, my mean would be in that middle there, but it would be pushed out a little bit more to include most of my data. My standard deviation would be a little bit farther out. The data is spread out more. When it comes to calculating both of those, we're going to use technology to do it just to save us some time. Remember, to get your average, you're finding the mean. So on Desmos, you can do this information, like this is an example, mean and the number set, and we'll give it to you. And standard deviation, same thing. On your TI calculators, here's some information about how you could also calculate both of those values there. With this section, we're mostly looking at identifying graphs. So for this example 3, they're saying, are these normal distributions? This first graph is. We can tell it fits that nice little bell curve. It's definitely a normal distribution. For the second graph, it's just all over the place. It's up, down, so that is not a normal distribution. On the third one, we see it's all pushed over to the right here, so it would be a skewed left graph, and this one would be skewed right because most of our data is pushed to the left. When we go back to this warm-up idea, they're asking who has the greatest mean. Remember, when most of our data is here, our mean was actually kind of back there on a skewed left, like the yellow graph, we could say. Remember, I'll answer this one. The yellow graph is skewed left, where the blue graph is skewed right. It feels a little bit backwards, remember? So the lowest mean, your mean for the green one is right here. Your mean for the yellow one is going to be about right here, and your mean for this one is going to be right here. So the lowest mean is on the blue graph, and the greatest mean is on the yellow. It does ask if you could draw a normal curve that's not skewed with a larger standard deviation than the green. So see how this green graph, it is a normal curve. Most of our data would lie within, like this one standard deviation might be like right here, because that's most of our data in there. Well, if I was going to draw a bell curve that had a greater standard deviation, I'd want to like flatten it out, if you will, like more data in between there. So there we would have most of our data would be in here. There's still our mean, but more of our data would be right there. That would expand our standard deviation. In lesson 11.4, we're going to use that normal curve and the distributions to see where data might fall and tell what that tells us about the data. So some vocab, a percentile, your z-score, and your standard normal distribution are going to appear. Now our concept summary that you guys have been filling out will have a lot of information that will seem quite foreign. So we're going to focus here in on this first empirical rule slide. So we have a normal curve here, and you're seeing lots of weird notation. This little U that you're kind of looking at stands for the mean. So they'll say over here that the mean is this little mu, they call it in Greek. Whereas standard deviation is that circle with a little swoop on the top. Okay, sigma there. So on these normal curves, we're going to talk about where the data lies. Most of your data here is right in the center of blue. And as a matter of fact, if the curve is normal, 68% of your data will lie there. So heights are maybe the easiest thing to relate to. If we're talking about the average height of a standard female, maybe we'll just say for ease sake that the average height of a female is 5 foot. Okay, so that's where anyone who is 5 feet tall would be placed and stacked up. All the people who have 5 foot as their height would be stacked there. Now, of course, there's people a little bit taller and a little bit shorter. So if we said this was our standard deviation was half a foot, so we'll say 6 inches. Now that means this would be 5 feet. This would be 5 foot 6 inches. Because when your standard deviation is 6 inches, that means it's 6 inches out both ways. So here we would have a 4 foot 6 inches. So anybody, say in a stadium or wherever, asking these females how tall they are, 68% of those females would answer that they're between 4'6" and 5'6". Now, as we move out a little bit, because your standard deviation is 6 inches, this would be 6 inches or 6 inches more. So here we'd have a 6 foot female. Now you can tell there's not as many people there, which makes sense. We don't have that many 6 foot females. And down here we would have a 4 foot female. Possible, but there aren't as many again. With this 95%, that means 95% of the females fall between 6 feet and 4 feet tall. And finally, if our example was true and we go another 6 inches out, we'd have 6 foot 6 inches for the third standard deviation and 3 foot 6 inches. So again, this is just made up general examples. That's probably not true. Pretty short and pretty tall for a female. But 99.7% of females say they're somewhere between 3 foot 6 inches and 6 foot 6 inches. It's important to note that when you're using the empirical rule, again, these numbers you're going to want to memorize, 68, 95, and 99.7. You're never going to be able to tell me this max value probably. We don't really talk about it. So those 0.3%, the ones that are outside here, very, very, very tall or very, very, very short, we don't really even have values for those. We don't go beyond 99.7%. So when we look at example 1, there's a great video if you're using the interactive textbook version here. But they say the example of the year 1817, they did a chest circumference of Scottish men. They said that it ranged from 33 to 48 inches. Now, the mean is 40, so on a normal curve, it's important you start to think about being able to draw these. We would put our mean right in the middle, 40 inches, and the standard deviation is 2 inches. So my first standard deviation out is going to be 42 inches, and then back one is going to be 38. 2 standard deviations out is going to be 44, and back 2 more inches is going to be 36. And then I could go to my third standard deviation and be 46 and then 34. So you'll want to be able to draw these curves, and now they're going to ask us about the empirical rule. Remember those percentages. There's a 68, a 95, and a 99.7%. The first question says, what range of chest measurements contains 68%? So remember that was the first standard deviation right here. Right here. So my first standard deviation, I'd have this first marking because I went out 1 standard deviation both ways. We'd say this one's between 38 to 42 inches. That's the range of chest measurements that they might have. Now, what would you expect the chest measurements to be for the 2.5% with the smallest? So smallest chest measurements are going to be down here, of course. But you might be saying, where are they getting the 2.5? If you had 95% in the middle, so here's where the 95 lies. Okay, this is the 95. You've got 5% left over. That's 2.5 out here and 2.5 out here. When they want the chest measurements in the lowest 2.5%, we're looking here between 34 and 36 inches. Again, on this try it, they drew the SAT normal curve for you. They want between 266 and 750. Notice 266 is here and 750 is here. This first standard deviation would be your 68, And then the second standard deviation would be your 95% of the scores were there. Now, if they want the 266 to 629, this one's going to be a little bit more interesting. So we know that there's 68% in that first standard deviation. We also want this percentage. So if 68 was here, but the second standard deviation is 95, we could take our 95 minus our 68. That would leave 27%. That means from here and here, there's 27%. So if we divide that by 2, we'd have 13.5 on just the one side. So that would be our 13.5 is from 266 to 387 of a score. And then we want to also add in that 68 because they all got a score from 387 to 629. So 68 plus 13.5, 71.5, right? That would be what percent of students got a score from 266 to 629. Now, working with normal curves is easy, especially if you're only talking about, say, just SAT scores or just female heights. But when you're trying to compare SAT to ACT scores or male and female heights, you might have a very tall female and a very tall male, but you want to know which one is taller for their gender. It's really hard to compare a female to a male height when you don't know what their averages are because the average male is usually taller than the average female. So we're going to compare scores for SAT and ACT. Note that they are different tests, so we need something called a z-score to compare them properly. Here's some information. You may want to take a moment to read it, but we would ask that you be able to draw a curve with this. Okay, so they have drawn the curves for us, the mean in the middle of the normal curves, and the standard deviations written out to 3 on both ways. So we need to look at this z-scores information from your concept summary. Okay, so it said you want to take your actual data value, like what score you got or what height you are, subtract the average, and divide by your standard deviation. This will give you how many standard deviations you are from the mean. So Alicia took the ACT, and we're going to use this normal curve. You follow the formula. Her score, take away the average, divided by the standard deviation gives her a z-score of 2.2. That means she's 2.2 standard deviations above average. Now, Ella took the SAT, so she got a 1380. Again, I followed the z-score formula, and she has a 1.9. So that means she's 1.9 standard deviations above average. Who did better then? Well, since Alicia's standard deviation is higher, that puts her further out on her scale. So that means she did better than Ella did, even though they took different tests. On the try it, you'd use those same graphs. And again, you know the score of 23. You would take that score, the 23, minus the average of 21, and then divide by that standard deviation of 5 versus the person who got the score of 11 and 20, subtracting the 1,000 over the standard deviation of 200, and it appears that if we did this, our 1120 has a z-score of 0.6, and our 23 has a z-score of 0.4, so the person who did better would be our SAT score. Now I'm going to go back to example 3 real quick to kind of give you a preview of what example 4 is talking about. You see Alicia scored right here with 2.2 standard deviations above average. Someone might ask, well, how did she do? How much did she do better than a lot of people? And you'd say yes. They might say, what percent did she do better than? We would say it's called a percentile. That's the number of scores that were below Alicia's. And you could say, well, most of them were. We know it's more than 68. We know it's more than 95. But what percent is it exactly? To find that, you're going to use either a table or technology to help you calculate what percent falls below her score. So to find this percentile, or the percent below a certain marking on your normal curve, in Desmos you can click Functions and click over on Distribution and Normal Distribution. Then type in your list of all the data values there, click on Find Cumulative Property, and type in your max number that you want to be. Say they have a 2.7. If I type that in and I had